Let me introduce myself. My name is Ajit Singh Rena. I am a Docker captain as well as Docker community leader in Bengaluru. And I will be your host for the entire tracks today, which is a mix of Docker for developers, open source, transform, and there are other tracks, other panels, discussions, all those are we are going to cover in today. So we will start with the first track, which is an open source track. And we have our first speaker who is working as a senior software development engineer at AWS. And he is here to talk about firecracker containerd projects. So if you are new to the firecracker, this is an open source project which was announced by Amazon in the last reInvent AWS, which happened in 2018. The speaker helped building the Amazon ECS and Fargate, and he's a contributor to Docker and Containerd project. Under this session, he's going to deep dive into Firecracker Containerd. So without any further delay, let us welcome Samuel Karp onto the stage.
Hi, everyone. My name is Sam. As I was introduced, I'm an engineer working at AWS, and I work on the team that is helping to build the Firecracker Containerd project, which is an open source project aiming to make it easier to run containers with hypervisor-mediated isolation, provided by the Firecracker VMM, which is a new virtual machine monitor announced by AWS at reInvent. So we have a little bit of an agenda for today. We're going to do a really, really brief overview of containers just because I want to set some context for what's interesting. Then we're going to dive into what is containerd and what is interesting from a container runtime perspective. We'll talk a little bit about the Firecracker virtual machine monitor itself. Then we'll talk about what it takes to convert that into something that is usable with containerd and usable for containers. We'll have a really short demo, and then we're going to talk about where the project is, and we'll have some time for Q&A. So I think you know all of this about containers, or most of you who are here at DockerCon are probably going to be familiar with this already, but I do want to talk about this just to set some context. Containers are a really broad term, but we're talking about the aspects of containers that are related to both the usability of containers, what makes them interesting from why you want to use them, and also the underlying technologies that are implementing containers. So containers, from a usability perspective, are primarily a mechanism for distributing and running software with varying degrees of isolation and repeatability. Containers have grown really popular because of the kinds of things that they've enabled, like repeatable deployments. Some of the problems that you might have with deployments are the drift in your different systems in terms of dependencies or in terms of configuration. Containers being an image-based deployment system with an isolated view of the system and an isolated view of the file system help to get around that issue by letting you package all of your dependencies and all of your configuration inside the container image itself. And that lets you know that the same versions of your dependencies are always going to be present. Containers are also efficient in storage and network transfer. Docker has helped to build this thing called layers, which give you a way to share some contents between different container images and only have to transfer deltas instead of the whole image every time you want to download it. There's also copy on write, so when you modify or when you launch a new container, you can launch it really quickly without having to copy the whole file system. Containers are also pretty flexible. You can have single-purpose containers and then compose them together to build applications out of a combination of containers, instead of having to package everything in a single container. You can have a separate file system, but you can share things like the network so that your different containers can communicate over localhost, or things like the Unix IPC subsystem. Containers make it easy to automate your deployments because of these kinds of repeatability. You can rely on containers to be deployed correctly. The separation of purposes in containers lets you have an application composed out of multiple containers. So you can have something like a web server in one container, your application code in another, and some monitoring infrastructure in a third. This composability is also both driven by and led to some of the popularity of container orchestration systems like Kubernetes or like Amazon ECS to make it easier to deploy and manage containers in production systems at large number of containers, large number of hosts. So these multi-container workloads end up making up the basic unit of deployment in the form of Kubernetes pods and ECS tasks. So containers on Linux are made out of a number of different primitives in the Linux kernel. There's enough here for a talk on its own, but I do want to touch on them briefly because they make up a lot of the flexibility of containers. So namespaces are a mechanism to control visibility and provide separation of things like networks or process IDs and file systems. Control groups, as they're commonly used in containers, help you to limit the quantity of resources that are used, like the amount of memory or CPU that a given container can access. Capabilities provide somewhat of a finer grained control over permissions than just a single root or non-root user. Seccomp is a mechanism for limiting the allowable syscalls that a process or a container can make. Linux security modules like SELinux and AppArmor provide ways to restrict access to resources like files. And finally, union file systems are the mechanism that image layers work with. Containers share a Linux kernel. The technologies that make up a container are really flexible, and the fact that these technologies are built into Linux make containers run really quickly with very little overhead. Virtual machines are a little bit more isolated. They virtualize or emulate hardware components, and you need to run a full operating system on top of the VM in order to use it. They also need to take care of the boot process, including things like initializing the hardware components. VMs typically have a little bit more overhead than containers because of that. So if VMs have more overhead, why would you want them? Generally, I think they're easier to reason about. Virtual machines have a single Linux kernel per virtual machine. They only have access to that individual machine. Containers, on the other hand, share a kernel. And that means that you're sharing the entirety of the Linux kernel interface, which can be something that's pretty large. You have all sorts of different syscalls that Linux has. You have data exposed in the proc file system and the sys file system. And it can be challenging to reason about all of the interactions between those syscalls and the data that's exposed. VMs, on the other hand, look like hardware. And when you're creating a virtual machine, you have the option of creating something with very simple hardware, with very straightforward interactions, with well-known hardware interfaces. That makes it easier to reason about from a security and isolation perspective, and a great place to establish trust and resource boundaries, which make it good when you run things like multi-tenant workloads, like what we do in the cloud, where we run workloads belonging to different customers on the same physical hardware. It also makes it easier to run workloads where you don't really trust some of the software. For example, use cases where you're transcoding user-submitted content like videos or audio or images with tools that have had a little bit of a spottier vulnerability history. So what do I mean by isolation? In AWS, we believe that our first responsibility is security of the infrastructure, protecting against infrastructure-level attacks. We have what we call a shared security model, where we take responsibility for the underlying infrastructure and customers are responsible for the security of their own applications. And that means that we need to protect customers from other tenants that are running on the same hardware. And that can be things like customers that are intentionally malicious and are intentionally trying to attack other customers, or things like noisy neighbor problem, where you have customers that are using a lot of resources. And so we don't want someone who's using all of their resources to affect you. AWS believes pretty strongly in defense in depth, and what that means is we have different mechanisms to protect against multiple different kinds of threats. We use a classification system called STRIDE for thinking about different kinds of threats, and STRIDE stands for spoofing, tampering, repudiation, information disclosure, and escalation of privilege. When we build an AWS service, we end up constructing a threat model that covers threats in all these different categories, and we come up with mitigations to try and deal with those threats. The Linux primitives that make up containers are not very new, and you can use them to increase the isolation or enforce separation of processes. You can use things like seccomp to limit syscalls, you can use Linux security modules, but because they share a kernel, the kernel is a single point of failure. It wasn't really necessarily designed with these use cases in mind. And the flexibility of configuration that containers have make it easy to accidentally expose threats like tampering, information disclosure, and escalation of privilege. In the cloud, we've relied on hypervisors and virtualization for a pretty long time. We believe that hypervisors protect well against the kind of threats that containers can expose, and we're generally happier relying on a mechanism like that, which doesn't involve sharing a Linux kernel between different customers in the cloud. But isolation isn't really enough on its own. We want to meet our customers where they are and enable them to run all of the different kinds of workloads that they want to run. And over the past few years, Linux containers have grown increasingly popular due in large part to the Docker toolchain and the easy user experience it's provided. And I think the fact that you're here at DockerCon probably means that you agree with me on that. Docker's immutable images, easy way to save and pass around those images, and easy command line interface have really helped to drive this popularity. Container orchestrators like Amazon ECS, Kubernetes, and Mesos have also grown in popularity as a means to run and manage large numbers of containers over lots of machines. And container orchestrators like this have made it easy to deploy multiple containers and compose them together as a single unit, like an ECS task or Kubernetes pod. As Docker has evolved and as the container landscape has matured, some standards have emerged. One of the bodies responsible for these standards is the Open Containers Initiative, a part of the Linux Foundation, whose members include the maintainers of Docker and various other parties interested in improving the container ecosystem. OCI has established a few standards that are relevant to container users and are particularly relevant to the firecracker-containerd project that we're talking about today. These include the image standard, which defines how a container file system should be represented and transferred, as well as the runtime standard, which is meant to make it easier to have alternative ways to run containers. Kubernetes has also established an interface for runtimes called the CRI, or the Container Runtime Interface. Compliant runtimes with CRI can be easily used with Kubernetes. So that brings us to container runtimes, or the software that hopefully makes it easy to run your workloads inside containers. When you run containers, you probably interact with a few different parts of the stack. And I've tried to break that down a little bit up here. You might interact with a cluster orchestrator like Amazon ECS or Kubernetes to coordinate containers across different hosts, handle application semantics like exposing services through load balancers, monitoring, scaling, all those things. You may interact with a local orchestrator like Docker for development purposes, and also many of the container orchestrators that you use end up using Docker to do local orchestration on the host as well. Docker ends up handling things like local restart policies, health checks, local network traffic, I/O, and collecting logs. Below the orchestrator might be a management component that deals specifically with the lifecycle of containers, like containerd. Containerd was a component that was broken out of Docker and factored to be a separate thing. And so now Docker uses containerd for local lifecycle management of containers. Most people might not interact at this layer. And below that is finally the container runtime, like runc, which is responsible for making the container actually work. Today, we're mostly going to talk about these bottom two layers, local management with containerd and the runtime. For standard Linux containers, runtimes are responsible for setting up the Linux primitives that make up containers, like cgroups and namespaces and the file system from the container image. The Open Containers Initiative has a standard for container runtimes, largely based on the work that Docker did, and runc was actually a contribution from Docker to the Open Containers Initiative. And runc ends up being the reference or standard implementation of the OCI runtime. But as a standard, the intent is to make runtimes swappable and that other runtimes can exist, other implementations can exist, like the one that we're writing for Firecracker. Containerd is a slightly higher level tool that builds management capability for containers, helps you control the lifecycle, manage container images, handle I/O, and so forth. Containerd was donated by Docker to the Cloud Native Computing Foundation. It's written in a very modular way, and that makes it attractive as a platform to build Firecracker support for containers. So let's talk a little bit about containerd's modularity. Containerd is broken up into a bunch of pieces which are intended to be independently usable, but also complement each other well when you use them together. As a user of containerd, or an implementer of an orchestrator like Kubernetes, the primary mechanism of interacting is through containerd's gRPC API, or an adapter layer like containerd's thick Go client. This diagram shows some of the components that we're interested in. First, we're going to talk about the content store. This is where containerd stores raw content, which is usually compressed image layers. When an image is pulled with containerd, it ends up in the content store. The layers of the image are typically stored as compressed tarballs and are not extracted into a file system in this component. Next, we have snapshotters. This is the component that is responsible for materializing the raw image content, that those compressed tarballs in the content store, into a file system that you'd see in a container. Copy on write functionality that you'll see in systems like Docker is implemented at this layer. If you've ever used Docker, you've seen its storage or its graph drivers. The snapshotters are basically equivalent functionality with some slightly different implementation choices. From an API perspective, each snapshot in a snapshotter represents a full file system. When you extract an image into a snapshotter, you end up with a snapshot at the end containing the full image contents. But the implementation inside the snapshotter can do whatever it wants as long as the thing that it exposed at the end is a file system that is the combination of its layers. Containerd has a few built-in implementations of snapshotters that offer different trade-offs in things like space or storage efficiency. The next thing I want to talk about is the runtime. This is where Containerd dispatches to a lower level runtime like runc. So the standard one that you'll use is runc, the reference implementation for the OCI standard. Runc implements containers using those Linux primitives that we already talked about. But Containerd can use any runtime that either adheres to the OCI standard or adheres to a separate version 2 runtime interface that the Containerd project has created that's intended to be a little bit more flexible at the expense of some additional complexity. Containerd also has a plugin system, which means that different implementations of these interfaces, of these parts of Containerd, can be loaded as plugins. For example, there are multiple snapshotters, and those can be either compiled in or they can be loaded at runtime. So I want to talk next a little bit about Firecracker itself. Firecracker is a new virtual machine monitor that was recently open sourced by AWS. It was built specifically for some of our internal infrastructure, like AWS Lambda and AWS Fargate, as a very small, fast, purpose-built VMM for running function and container-like workloads. Having a really small target use case means that the implementation has the freedom to cut out a lot of things that you'd see in a more general purpose VMM. Things like a floppy drive, or a full keyboard, or even things like a PCI bus. Cutting out unused components makes it easier to optimize both for speed and for security. And those are the goals of Firecracker. Firecracker is designed to be secure and efficient above pretty much all of the other concerns that we might have. Firecracker attempts to optimize for security by limiting the scope of what Firecracker can do in terms of the features that it has and the model it exposes to a guest virtual machine, and even the permissions that the VMM itself has to make calls into Linux. It focuses on reducing the ability for the guest VM to interact with the host kernel by implementing some of the functions that could be provided by the host kernel's KVM subsystem in the VMM itself. It also limits the ability of one guest to interact with another VM guest by sticking to a single virtual machine per VMM model, so a single process model. And we wrote Firecracker in a memory-safe programming language like Rust in order to protect against common programming errors like use after free and buffer overflows. Firecracker also aims for efficiency in terms of the guest boot time and the overhead of the VMM itself. The developers of Firecracker measure this as part of their continuous integration system. So they have targets for the boot time, the amount of time it takes to go from launching the Firecracker VMM to the guest VM having user space execute, as well as how much memory and how much CPU is consumed during the whole process. And Firecracker exposes an API to drive all of its interactions, making it pretty programmable. So for Firecracker Containerd, we're trying to run containers with Firecracker, and we do have some goals for the project. The first is that we want to be compatible with the things that people are already doing with containers and enable them to use Firecracker without having to make major changes to either their software or their workflows. This means we want to support people's existing Docker or OCI container images. We also want the resulting containers to look a lot like you'd expect when you weren't using Firecracker in terms of the kernel surfaces exposed inside of a container. By that I mean we still want to use C groups and namespaces and mount in the proc file system and mount in the sys file system with the goal that existing monitoring and debugging tools can still be used with Firecracker. We want to support composable applications, containers that share namespaces or volumes like you'd see in a Kubernetes pod or an ECS task, and we'll do that by running multiple containers inside the same virtual machine. And since I mentioned orchestrators, we'd like to integrate with orchestrators like Kubernetes and ECS. We also want to minimize the additional overhead as much as we can so that there's not so much extra latency in starting a container or extra CPU and memory being consumed. From a security perspective, the main idea is to leverage all the work that Firecracker is doing for us. This means hypervisor-based isolation, and also means that there are limits to accessing the underlying host. So we do have some competing goals: compatibility, but also limited access to the underlying host. And we're still figuring out if we believe that there are safe ways to do things like exposing volumes from the host into the guest VM and subsequently into a container. But we'll talk a little bit more about that later. So how do we make Firecracker look like a container runtime? We need to adapt to the limited feature set supported by the VMM. These limited features are in the name of making it easier to reason about from a security perspective. So we have container images that we store on the host in Containerd's content store, and we need to expose those into the VM guest so that we can actually run containers. But guest VMs can't share any file system with the host. This means that we need a different approach for exposing the root file systems, and we'll do so as block devices that we attach to the VM. Firecracker doesn't support hot device attachments, so we need to pre-allocate the number of devices and the kinds of devices that we need, including the devices that we use for presenting those file systems. Containers are usually configured for networking with a virtual Ethernet or a vEth pair that takes traffic from one Linux network namespace and exposes it into another. Firecracker supports networking through a Linux tap device, so we plan to make that tap device easily usable with a networking plugin like CNI through a technique called TC mirroring, the Linux traffic control subsystem. And our preferred way to communicate from the host to the guest is via a technique called vSock. This we need in order to control the containers that are running inside of the VM from outside the VM. So what we ended up doing is we built a block device snapshotter, a plugin to manage the VMM, a runtime to manage containers from the host, and then an agent inside the VM guest to actually run the containers. So this is a diagram trying to show a little bit about how the Containerd and Firecracker runtime creates Firecracker micro VMs and runs containers inside of them. The architecture consists of 4 main components: the snapshotter, control plugin, runtime, and the agent. The first we're going to talk about is the snapshotter. That's responsible for exposing the file system to the container inside the micro VM. We wrote a block device-based snapshotter that we're able to attach block devices to the micro VM. The snapshotter currently runs as an out-of-process gRPC proxy plugin, so it's an independent process that can be used with Containerd without having to recompile Containerd. The next component up here is a control plugin that we're writing in order to provide an API for managing the lifecycle of the virtual machine itself and linking Containerd to the Firecracker virtual machine monitor. It's responsible for configuring the parameters for the virtual machine and it uses a disk image that contains the VM root file system as well as the kernel for the guest. The control plugin is currently implemented as an in-process compiled-in plugin, which means we do have to compile a slightly different version of Containerd in order to use it. We also built a runtime that's responsible for linking Containerd outside the VM to the components that are running inside the VM. The runtime primarily acts as a proxy and is responsible just for passing data through. The runtime is implemented as an out-of-process shim runtime, communicating over a vSock device into the virtual machine. Last, we have an agent running inside the micro VM, which is responsible for mounting the snapshot images and invoking the containers, and it does that via runc in order to create standard Linux containers inside the micro VM. So let's talk about each one of these in a little bit more depth. First, we're going to talk about the block device snapshotter. So snapshotters are Containerd's way of creating a usable root file system from a container image. For Firecracker Containerd, as I said before, we store the container image on the host, not inside the guest. And so we need to have a way to expose the root file system into the guest VM. Firecracker does not have a mechanism to share file systems between the guest VM and the host, pretty much for security purposes. We don't know of a way that we're comfortable doing that safely. So we need a different way to expose the container file system that's based on an image into the VM. And we do this by creating block devices that contain the file system and then attaching them to the VM with the Firecracker API. Inside the VM, we then need to mount those block devices in order to make them usable to the containers running inside. There are a bunch of different ways to implement snapshotters and a bunch of different ways to do block devices. So we ended up writing 2 different ones. The first one that we wrote is called the naive snapshotter, and it was really implemented as a proof of concept, a way for us to continue developing the rest of the system. It works very simply. It creates a flat file. We create a file system within that flat file, and then every time we want to make a new layer or make a new container, we have to copy the whole file and write the new stuff into it. That means that we're doing copy ahead instead of copy on write, and it means that we have overhead when we're starting containers or overhead when we're pulling images in terms of both the amount of disk that's used and the time that it takes to do the copy. The second one that we've implemented is one that we're more interested in actually running in production instead of just a proof of concept, which is a device mapper-based snapshotter. This one's somewhat similar to Docker's device mapper, storage, or graph driver. Both of them rely on a thinly provisioned pool of devices or pool of storage, and then expose that storage as a device. So the thin pool allows us to share blocks between multiple devices to deduplicate storage, and that means that we do actually have copy on write behavior instead of copy ahead behavior. And it makes it a lot faster for us to both pull images and for us to start containers based on those images. So we ultimately contributed the device mapper snapshotter upstream to the containerd project, and we expect it to be released in the next version of containerd that comes out. After that happened, there were 2 more implementations of block device snapshotters that have started to emerge from others in the container community. The first one is an LVM-based snapshotter. The LVM snapshotter is somewhat similar to device mapper, but uses a different implementation for doing that. It does look interesting because it has many of the same advantages that the device mapper snapshotter will have. And so we're going to continue to look at that and evaluate it and see whether it's more interesting to us than the one that we wrote. The last one that's up here is called rawblock, and is a little bit different. Instead of using just devices that it manages either through LVM or device mapper, it uses a file system feature called reflink. And reflink is a feature in some file systems like XFS and BTRFS that allows for copy on write of files where the blocks are tracked between the copies. So if you make a reflink to a file, but nothing is modified, you don't duplicate any of the storage. But as soon as you modify things, it only duplicates the block storage that's there. I don't think that we're going to look too hard at the reflink snapshotter because it's not supported on all file systems. Reflink isn't a feature that's available everywhere, and we want firecracker-containerd to be usable with file systems like ext4. So next I want to talk a little bit about the control plugin. We're starting to build this new Firecracker control plugin for containerd to help manage the VM-specific settings, like which kernel to use and what resources to allocate in terms of memory and CPU and devices and so forth. Along with holding information about how the VM itself should be configured, this is intended for the use case of running multiple containers inside the same VM. We can't really embed the lifecycle of the VM in containerd's container or task APIs that it already has. So this is a new API that we're adding in order to have that as a separate object. We are making it specific to Firecracker right now, just so that we can get the workflow working and proven, but we're also interested in talking with the containerd maintainers more about what it could look like to have a more generic group of container API or sandbox API that would be native to containerd. And if that's something that the containerd project is open to, we're interested in helping to contribute that. The control plugin is a compiled-in plugin right now, meaning that it doesn't work with the standard containerd binaries, and it does that only because that is a mechanism that made it easier for us to add the API over containerd's existing socket that it exposes and not require clients to have a different way of connecting to it. But we're looking to see how we can change that in the future and either run it as like an out-of-process proxy plugin or a dynamically linked Go plugin if that's something that we can do. So next I want to talk about the runtime. This is the component that runs outside of the VM and is responsible for proxying instructions to the component that runs inside the VM, the agent. It's responsible for taking commands and also the input and output streams for every container that runs. proxying events that happen, like a container starting or container stopping, and proxying things like metrics from within the VM to containerd outside. We implemented this with containeرد's v2 API instead of the OCI standard, as we felt like it gave us a little bit more flexibility in how we can implement the runtime. The OCI standard, which is what runc implements, is essentially tied to a single process per container model because it specifies a command line interface for operating with containers. Containerd's v2 API instead gives us the ability to choose how many processes we need, and that lets us make choices that simplify our architecture. We're implementing a model where we have a single runtime process per virtual machine, and it's responsible for all of the containers within that same VM. So finally, I want to talk about the agent. The firecracker-containerd agent is responsible for managing the lifecycle of the containers that run inside the VM. It's the other half of the runtime, and it receives commands from the runtime that we wrote outside the VM over the vSoc device. It also is responsible of doing the other half of proxying the I/O streams for each of the containers and actually sends the events and metrics. We use runc inside the VM in order to manage the containers, setting up all the things that containers would normally expect, like C groups and namespaces, so that it still looks like a normal container when you're running inside. The agent component is also responsible for mapping a given block device to a given container. Firecracker doesn't currently have a mechanism to expose which block device is which, so we're working on approaches that map each block device to the appropriate container and its file system. And we need to do that because the block device contains the file system for a particular container. So now that we've talked about each of the components, let's take a look at an example of how they work together to run a set of containers inside of a micro VM. So we'll start off with storage management, or what's involved in exposing a root file system for a container. The orchestrator or client program, which can be something like the Kubernetes CRI or ECS, starts off by making a request to containerd to create a snapshot from an image. Containerd then passes this request along to a snapshotter implementation. The snapshotter then allocates a snapshot and responds back with an identifier for that snapshot. Containerd acts as a pass-through here, and you'll see that containerd acts as a pass-through for many of the API actions that we're interested in. Once we have all the snapshots created, which we need as block devices, we can launch a VM. The orchestrator makes a request to the control plugin that we've written, asking it to start the VM. The Firecracker VMM is designed to run a single virtual machine, so we need to start a new VMM process for every VM that we want to run. Because Firecracker needs to know what devices to use up front, we need to include that information in this request. We'll pass in placeholder devices at this time, but an equal number of devices to the number of containers we want to run, because each of those devices is going to hold the root file system for one of the containers. Once the plugin has started a new Firecracker process and asks it to run a VM, it returns an identifier back to the orchestrator. Now we can start to run some containers. The orchestrator makes a request to containerd's container and task services to run a container. Containerd passes those through to the runtime, which we've written for Firecracker. In the request, we include both the VM ID that we want to run, as well as the snapshot ID that should be used as the container's root file system. The runtime will then invoke the Firecracker API to attach the device, and then ask the agent to mount the device. Once the device is mounted, we can then ask the agent to start runc and launch the main process of the container. When the container starts running, we'll return all of that information all the way back out to the orchestrator. The orchestrator will probably want to know about what happens to the container so it can subscribe to events. At some point, the container process might exit because it's finished with its job, or it has an error, or it's been told to exit. Exits will be observed by the agent and propagated out to containerd. Because the orchestrator has subscribed, it also gets a copy of the exit event. When all of the containers have exited, the orchestrator can make a request to the plugin to stop the VM, and the plugin can then terminate the Firecracker process. And that's it. So I have a really brief demo that's more of, we captured some output and put in some slides. So it's not quite a live demo, but this is what it would look like. This is showing how you can run a container using CTR, which is the development tool for containerd, and the standard runc runtime. And what I want to show you is the difference, what it looks like from the host's perspective of running a container versus running a Firecracker micro VM and the containers that are running inside. So what we're doing here is we're running a container that is the stress program, which is a fairly common Linux program, and we've configured it to use a total of 6 processes, 2 that are consuming CPU and 4 that are just churning on I/O. Once we have stress running, we can examine the running state of the system as viewed from the default process namespace. And we can see the stress program and its constituent threads viewed as normal first-class process objects. Beyond seeing them just with pgrep, we can go ahead and look at the inheritance. We can see what is responsible for starting what process. And if you look, you can see all the way on the right the individual threads that are part of the stress program. And you can see that it's started by an entry point, and that's started by the default containerd runc shim, which is then started by containerd. So this is what it looks like to just run a normal Linux container and look at the processes from the host's process namespace. Now we'll see the same stress container, but inside a Firecracker VM with firecracker-containerd. And you can see that there's a couple differences in this command line. It's mostly the same, but we've got 2 things there that are specific to Firecracker. The first is we've specified the runtime as the Firecracker runtime that we've written. The second is that we've specified one of the block device-based snapshotters. And this is so that we can expose that file system to the container. But other than that, it's pretty much the same thing. It's also running through CTR, and it's also like pretty much the same command line. If you inspect the running state of the system as viewed from the default namespaces, you can see that there is no stress command visible, there is no stress program visible, and instead you see a Firecracker process running. And if we go look at this, looking at the inheritance, you can see the same sort of thing here, is that we have all the way on the right is the kernel threads that correspond to the Firecracker CPUs that are exposed in the VMM itself. Then there's the Firecracker process that was started by the containerd shim that we wrote, and that's ultimately started by, in this case, it's started by the init system. And if we go ahead and look at this, even though we can't see the stress process, we can see that it's still consuming resources. And the resources at this point are just attributed to the VMM itself. And so the host doesn't have any visibility into the processes that are running inside the VM. Similarly, the processes running inside the VM won't have any visibility into the host. And so we've created a little bit of a harder security boundary there than there is just with normal Linux containers. So I'll talk a little bit about the current status of the project. It is an open source project. A lot of it all works, but we're still in the prototype or proof of concept stage for a lot of the parts of it. We do know where we want to take it. We want to make it broadly useful for running containers with a VM boundary and a separate kernel instead of standard Linux containers. And we also want to make it easy to do workflows that people are using with things like Kubernetes, where you're running a bunch of containers together and you want them to share some resources. So we do have a few tactical things that we're working on right now. Like Firecracker's vSOC support right now is experimental and is not the final implementation that they'll end up with, so we'll need to move away from that. And we also need to work on that block device identification issue that I talked about earlier, where a block device that contains a file system has to correspond to an individual container. But all of these are supporting the goal of helping us run multiple containers in the same virtual machine, workflows like the Docker exec, where you can launch a new process inside the same container, and then things like health checks and metrics. The biggest thing that we see that containerd is missing right now is an API for groups of containers. And I talked about this a little bit earlier. Groups of containers that run together is required for running things like Kubernetes pods or ECS tasks. Mostly that's been implemented outside of the container runtime. So there's a plugin for Kubernetes in containerd called CRI containerd, and that implements a grouping logic itself instead of delegating some of that down into containerd. But groups of container are also useful when modeling security boundaries. We want the containers that are grouped together to share the same boundary. We want them all to run together. And so for us, for Firecracker containerd, we need an API to manage what is that group and what are the containers that belong to that group. So this is the thing that we've built as the control plugin right now that's specific to Firecracker. But it's something that we're interested in helping to contribute upstream to containerd, a way of grouping containers together and having that as an API object that's modeled in containerd. Longer term, there's still things that we haven't really decided how we're going to implement, either because we're not sure or there's competing proposals. Some of these things are challenges because of our desire to keep Firecracker's very minimal device model and feature set in order to help Firecracker and firecracker-containerd make the arguments about security boundaries. So a big one that we're trying to figure out how we're going to do is CRI conformance. The CRI, the container runtime interface part of Kubernetes, is a little bit more flexible and doesn't fully specify all of the containers that are going to be launched together in the same group, the same pod, or the same sandbox. And that makes it hard for us to properly size the virtual machine at launch because we don't know how much CPU or how much memory is ultimately going to be needed by the application that runs in there. We also don't know how many containers are going to run, and that makes it challenging for us from the perspective of needing to allocate the block devices ahead of time. And Firecracker doesn't support dynamically attaching new block devices or dynamically changing the size of a VM once it's been launched. So these are things that we're going to need to work out for CRI. CRI also requires some file system sharing for pods. This is for things like the Kubernetes downward config, for secrets and things like that. And because we don't have file system sharing from the host to the guest, that's another thing that we're going to need to work out and figure out what we're going to do in terms of conformance there. A typical way that this is done with virtual machines in other systems is the 9P file system protocol. You'll see that if you use QEMU or the Kata containers project, but Firecracker doesn't plan to support 9P, so we're looking at alternative approaches. One that's interesting to us and that we haven't finished evaluating yet is VirtIO FS, which is a fused file system that communicates over the VirtIO device. But we're also looking at other approaches like perhaps doing local NFS if we have to, or other ideas. So firecracker-containerd is an open source project. It's also something that we're developing ourselves. So we're happy if you want to get involved, but it's definitely not something where we're asking you if you're not interested in. I just don't want to come up on a stage like this and be a big company asking for contributors. So if you're interested, we're more than happy to have you help, but if you're not, like, this is not a request for help. And that can be as simple as using it or reporting bugs, or as much as like coming to work with us and joining our team. Our GitHub repository has all of our code, and we're trying to put our design documents up there as well. We also hang out in the Firecracker Slack in the containerd channel. So that link up there, the second one, is a link to get an invite to the Firecracker Slack, and you can reach us there. If you're interested in working at AWS, come talk to me afterward. The containers group is hiring across all of the services that we have, like ECS, EKS, ECR, and Fargate, as well as the lower level infrastructure like our team. So I think now it's time for questions if you have any.
Yeah. Any questions?
How will you compare gvisor versus Firecracker?
So the gvisor is a bit of a different technology. I definitely can't claim to be an expert in gvisor, but my understanding about it is that it's attempting to re-implement the Linux kernel in Go or in a different system. So we took a different approach. Re-implementing the Linux kernel means that you are responsible for ensuring that your system is compatible and ensuring that the behaviors look like Linux. From our perspective, we think it's a little bit easier to just let Linux be Linux and focus on the things that are interesting for us in terms of containment and isolation instead of re-implementing it.
Are there any plans to make it so that Firecracker can do the dynamic block, mounting and that kind of thing?
I would have to defer to the Firecracker team for that a little bit. I don't think it's in their current roadmap right now. Having it be configured only once at startup makes it a lot easier. It's very simple code paths for them, and they don't have to implement things like a full PCI bus to do hot plug. So adding that is more in terms of code complexity and more in terms of what has to be thought about from a security perspective. So I don't know whether they're ever going to do it, but it's not in the current plans.
Great presentation.
Thank you.
A quick question. How do you control the kernel version of this micro VM?
So the kernel is, you can choose that when you're launching the micro VM. Firecracker just takes an ELF formatted binary as the kernel. And so if you have an uncompressed kernel image that's an ELF formatted binary, you can use it. There are some special requirements that Firecracker has around the kernel. Like it doesn't support compressed kernel images, which is what you'd normally see in a Linux system. It also doesn't support things like an initial RAM file system. So there's some different configuration choices you'll have to make, but you can use arbitrary kernels with it. Actually, you can also run non-Linux things with Firecracker. So we've seen some contributions from like unikernel projects that have been able to get their systems running with Firecracker as well, and that's pretty interesting too.
Thank you.
There are a couple of CRI plugins which manage or launch VMs. Do you see any room for standardization on managing the lifecycle of VMs, or is it too implementation specific?
I think that there could be some room for standardization. I haven't looked enough at the other CRI plugins yet to know what exactly is different between those and what we're looking at. We do know that we need to, there's specific things that we want to do from a Firecracker perspective, and so we want to make that a thing that we're doing first. But we'll look at those as well.
Thanks.
You mentioned near the beginning that you didn't want to implement a PCI bus for the guest OS. How do you enumerate the I/O devices without a PCI bus?
I don't know enough about Firecracker itself to answer that question. So that's a question that you can ask in the Firecracker Slack or in the Firecracker GitHub repository, and the maintainers of Firecracker will be able to answer that.
Thank you.
Yep.
We can take up one more question.
Hi, just extending on that unikernel question, there is a fundamental difference between what Firecracker does and how unikernels build out their VM and deploy. They, like you probably know, the attack surface of the kernel itself is much smaller. Why did you go with adopting a full kernel as opposed to a more optimized kernel for this sort of an architecture?
So for Firecracker, our goal is to enable the kinds of workloads that people are already running, and most people that are running workloads are running them in Linux today. So we're trying to enable people to run their existing containers, or when Firecracker is used in AWS Lambda today, and we want people to run their existing Lambda functions in there. So we chose that because we're interested in compatibility and with what people are already doing. Unikernels are interesting. They've got a lot of cool technology behind them, but they are pretty different when someone is using them, and they require you to go through changes to adapt in order to use the unikernel itself.
If you have any further question, maybe Sam will be here. You can take it offline.
Yep.
We have a next presentation at around 2 o'clock, and that will be from SOM to Kubernetes and back again. So see you there.
Cool. And so one final thing before we go. I think there's a session survey. I would love if you filled it out and gave me feedback, things that you liked, things that you hated. But please keep in mind for both me and for all of the other talks that you're going to go to today that all of the presenters are humans. I'm going to be available just right outside right now. I'm here the whole week. So if you didn't get a chance to ask me questions right now, please come up and find me. If you don't have a chance to find me, my email address is up there and also my Twitter handle if you want to reach out to me that way. But yeah, thank you.